Okay, so the thing about this unit is, first of all, everything's extraordinarily long in terms of the amount of drawing. So this is a bit tedious. Like it's tedious for just the amount of marks that you're going to get here. And it's very easy to make mistakes when you're counting your atoms, to miss something or to make a bond wrong. So you got to be very careful throughout this process and a little bit meticulous. And so I'm going to go ahead and get started. Polyhydroxyamide is a fire-resistant polyamide, and it's given by these two monomers, F and G. And they ask you to draw the repeat units. And the amide bond should be shown displayed. So first of all, what is the amide bond? That's the amide bond right there. This is what they're saying. This part right here should be fully displayed. The C double bond ON, that should be completely written out. Everything else can be done in skeletal or structural as you wish. And so what I do when I'm doing all of these questions, I'm going to do this throughout the lesson today just to kind of like coach on how you should draw this, is I draw them out right next to each other, but I fully display the groups that matter, which is the COOH of the dicarboxylic acid. And for the other one, it's the NHH of this one. And so what am I supposed to do when I merge these two molecules together to go from a monomer to a polymer? Because right now they're separate. What should I be taking out? The OH from the carboxylic acid and the H from the that should be leaving. So a few of you left the oxygen in the middle, and that would give a wrong answer. So here you're going to take out, again, the OH from the side. So this is supposed to get out on this end, and this H is supposed to get out on that end. So you're taking out the water in the middle, and then you're taking out the water on the sides again. And so that gives you a double bond O. And yes, some of you can do this in your head, but I need to visualize it. C double bond O. And, which you don't have to write the H displayed. You could write it next to it. But I'm going to go ahead and write it displayed out. And that's it. So you should have gotten this as your response. You double check your answers to see if there's anything that you missed. A lot of how to do this right is facing your atoms, like rewriting it and facing the atoms that are actually doing the reaction towards each other so that you can see what happens from there. And so I'm going to go on to the next one. This one everybody got right that I checked, which was an addition reaction. We know that for an addition reaction, all we break is the pi bond, the double bond, and then we form new sigma bonds. So sigma bonds are the bonds formed. These are nice marks. 1 mark for each check mark in the right place. That's about as easy as a question you could possibly get, as long as you know what's being talked about here. And then here, this one's asking about intermolecular forces, which was in the homework. In the homework, it was an older question, and they just mentioned the word forces. And so what you're supposed to remember is your main intermolecular forces being IV. And what's that for? If I've got nonpolar molecules, right? PD is polar, and then H bond or hydrogen bond is if you've got H directly connected to fluorine, oxygen, or nitrogen, one of those three, yes.
Hey, what if peptide bonds become something different?
A what?
A peptide bond.
So no, a peptide bond is not an intermolecular force. I don't believe I've uttered the words peptide bond yet. That'll be in today's lesson, right? Today's lesson has peptide bonds in there, but the peptide bond itself is this. This is the peptide bond. It's the same thing as the amide bond. The peptide bond is the amide bond, the bond of the amide. We call it a peptide bond when what we're linking together are amino acids to form something called proteins. So this lesson today is actually going to be something that goes into biochemistry a little bit. So anybody who is planning on pursuing ACE biology next year needs to tune in to this lesson, because this is going to help you understand those ideas, because in biology, it's presented as a bunch of information, but this class kind of gives you how everything really links together. And so it gives you the foundation that you can then build up on. So save these notes if you're heading to either ACE Bio or if you're heading to like a college level bio class after this, because it really helps aid in understanding. So anyways, intermolecular forces, the two that should be pointed out is the first one would be hydrogen bonding. And the groups involved, you could either point out what the atoms are, or you could just say what the group is. It's the amide, but it's really that NH going on. That's really the part that's giving you the hydrogen bond. The hydrogen connected to boron, oxygen, or nitrogen. And then the other intermolecular force was ID, which you're allowed to use dispersion. In the older mark scheme, so in the homework, you're going to see that they say van der Waals in that question. You should use the newer terminology now, which is the ID or the dispersion. I pointed out in the answer key because I have some questions that are like 2014, 2015. So since older terminology, I'm trying to go back and point out, well, this is the new way that we would say it. So it's ID or dispersion. And then the group involved for this, you could just say benzene because it's the ring. And so that was 2 marks actually. So again, these marks are not too stressful, but the thing is, this actually comes from AS chemistry. There's another question, the last question of your homework, that talked about OSO4. I saw a lot of people left it blank. They said that OSO4 acts the same way as KMNO4, cold dilute. So some of the oxidates today will be working on putting together some flashcards for us, so that you'll be getting a new pack of flashcards really soon for your reactions. And you may want to take out your ones from last year, because as I might have mentioned before, any AS chemistry reaction can and does show. It's not frequently, but when they're presented like you know what they're talking about. So cold dilute KMNO4 was in the homework. If you are unsure how to solve any of the questions from today's homework or the one coming up, remember there's tutoring today after school, and then again next week on Monday will be the next day that there's tutoring. All right, so that's the homework review. Today we're going to be going over 2 big things. One of them is a reaction that we'll start putting on flashcards next class, but we're going to practice with it today. It's called hydrolysis. And so we're going to review hydrolysis reactions and why they're important to us. And then we're going to learn about biochemical polymers. Yes. Thank you. I believe I am, but let me double check. Yeah, it's recording. Wait, is it not recording? Manage recording. Yeah, it's being recorded. Thank you. All right, so we're going to go ahead and get started. Objectives. There's only 3, and actually there's only 2. That's a little scary. There's only 2 objectives today, but there's a lot to fill in that's technically like in other objectives, but it still has to be filled in for you to understand these. So what we're going to be doing today is describing the acid-base properties of amino acids. Well, first of all, you're going to have to learn what is an amino acid. And the last time you probably heard amino acid was when you took honors bio or pre-ACE bio. So we're going to represent to you today what is an amino acid. And then we're going to learn about something called the formation of a Zwitter ion. And I believe that is a German word, so it's a Zwitter, like that. Zwitter ion. To include the isoelectric point. Those are big fancy words we'll learn about in a little while. Then it says, describe the formation of amide peptide. Notice how I had said earlier that peptide bonds were just amide bonds. Literally, they're saying that in the objective from Cambridge. Between amino acids to give dipeptides and tripeptides. Interpret and predict the results in electrophoresis. We will not be able to do this today. This is going to be Thursday's lesson. But we are going to begin to talk about at varying pHs, what do amino acids look like? So if I had a low pH or high pH, what an amino acid look like? And then next class, we're going to talk about how to separate amino acids with a specific process called electrophoresis. Electro means electricity. So basically, you're putting electricity through the device. So we've got a few things to talk about today. See if I made notes here. Let's review something. Acid-base reactions. If I am going to react, let's say I have X minus with an acid, what do I get from that? What's my product? Add some.
HX.
Just HX. So this would be whatever I have operating as a base. Because bases accept H pluses. And then what if I had an acid and I wanted to react that with a base? First of all, what would I be reacting HX with to react it with a base? I'd be reacting it with OH minus. So what would happen if this is an acid? What would my products be? Add some.
Maybe I think H2O and
Water's one of them. And the other one? Just X. X minus. So one of the things you got to remember that's really key is that this is H plus and that's X minus, right? So when you are left with X, you're not just left with X with a regular, like with no charge. X has a negative charge. And you're going to have to remember that when we're looking through reactions later today. I'm also going to briefly go over acidic functional groups and basic functional groups. And neutral. What Cambridge wants you to know is a neutral functional group. So, acidic functional groups. Oh, what's the first one?
Oh.
What's the legality?
The main one, carboxylic acid, right? So COOH on molecule is an acid. There's another one that I haven't taught you yet, but I'm telling you about today because I did your homework and it shows up in the homework on at least one question. And I think I might have put it in the lesson too afterwards. This right here is acidic. This is a new group you have not seen before called phenol. Phenol is acidic. And although I was thinking about it, reflecting, I'm not going to teach all of the reasoning at this point because that's technically a Unit 6 topic. The concept is that the electrons, the localized electrons in the benzene ring are actually pulling electron density away from, like the electrons are being pulled away from the OH group. And what that does is if this part gets more negative, then the hydrogen is more positive. Technically the bond's weakened and the hydrogen could go away as an acid. So phenol is an acidic functional group. And that's basically a benzene ring that has an OH in it. It is not the same as a regular alcohol because of the delocalized electrons in the benzene ring. We're going to learn a lot about benzene. That's actually what the whole last unit is about, is reactions of benzene, pretty much. Yes.
We're gonna have to remember a bunch of new functional groups.
A few. And I've been starting to present them. Basic functional groups would be, there's literally only one major one you have to know, and it's amine. NH2, it's a derivative of ammonia. If you were to take the pH of ammonia, it's like a 10 or 11 pH. It's definitely basic. And then I know that we talked about, I think it may be a source of confusion, alcohols themselves are slightly basic. So you may want to say alcohols are slightly basic. But for the majority of what we talk about today, they will not be gaining an extra hydrogen in their reactions. They largely are close to neutral. If you look up the pKa of an alcohol versus the pKa of water, it's actually extremely similar. It's something like 16 and 15.7. It's so similar and barely changed. Like it's barely a base. Lightly. Like a base. And then neutral. You are going to need to know for the purposes of the topic today, for some of the homework questions, that amides are neutral. So although amines are basic, this is what you're going to have to watch for. Amides are neutral. They've got a part that's basic, that NH2 group, but the CO is pulling electron density away, which actually would make it more like an acid. So because it's got both the features of an acid and a base, that's why amides end up falling into the neutral category. So just FYI. This you should know for later on in today's lesson. I'm pointing it out now just so that we can go back to it later. Yes.
Why is amine basic?
Amines are basic because this NH2 can accept an H plus rather readily because of this.
And the oxygen also
For which one?
for carboxylic acid.
The factor that's the more important one here is that O pulling everything away. That ends up being a bigger factor. And you can always head back if you're unsure, look at the pKa values, because those are like the established experimental values that say this is what's stronger, this is what's weaker. And then later on in Unit 6, we're going to do more of the chemistry behind what makes a group acidic or what makes a group basic. Here I'm just presenting this to you so that you know it to be able to solve questions. But we are going to have to explain why some groups are acidic and why some groups are basic in Unit 6. Unit 6. Which is our final unit of study. All right, there's a couple more functional groups that I want you to know. I think I mentioned these last class, but I want you to know them and their naming convention. Yes, Edsel.
Are aldehydes and ketones still?
Ketones, by definition, don't have a hydrogen themselves. So, Na. Like the hydrogens that would be connected to the carbon with the ketone are super, 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 super weak acids. And by super weak, I mean their pKa is like 50, which means they're actually probably better bases. All right, so acyl chlorides is your first new group you really need to know. I mentioned it last class. You're looking here for COCl. And think of acyl chlorides the same way you think of carboxylic acids without having the acid part. They do almost all the same reactions that carboxylic acids do, except for acid base. And this is actually more reactive than the OH group. So what people will often do, chemists, is they'll turn something into an acyl chloride to make it more reactive. They'll make it more reactive so that they can get whatever it is, like they're trying to make a medicine and they need to do a reaction. It's better because with the acyl chloride than with the carboxylic acid, you get a higher yield. And so that's why Cambridge is presenting for us to be able to know what these are. And their naming conventions. You count the carbons and you change the ending to oil chloride. So what would the name of this be? I left it for us to work on purpose. This is what? There's two carbons here. So it's ethanoyl chloride. That's the name of this. Ethanoyl chloride. And so whenever I see this oil chloride, that means that I have a acyl chloride going on. And you should be aware of that naming convention. And then for amides, let me just give you a random one. CH3, CH2, CO, NH2. You only need to be able to name straight chain amides at this point. So what would the name of this be? It says the convention is to change the ending of the name to an amide. So what would this one be? Just count the carbons.
Hexanamide.
No, not F.
Economic.
1, 2, 3. Propanamide. Propanamide. 3 carbons, and it's got the amide group. So just general basic naming conventions for oil chlorides, which are acyl chlorides, and amides. So then we go on to the first major thing we need to know, which is technically review from AS chemistry. Partially review at least. Okay. So, hydrolysis. Go back. Hydrolysis is a reaction we learned in AS chemistry. And you need to access your old data files from like, I think the last time we looked at this was like 8 months ago. So if you deleted those data files, get out your flashcards or your notes from AS chemistry, because hydrolysis is a rather major reaction in the A-level class. That's why we're going to spend time going over it. There are many questions with it. And so what does hydrolysis mean? It means break apart with water. Literally, it is the opposite process of condensation. So you may want to write that. It's the opposite of condensation. And we mentioned last lesson at the very, very end that biodegradable polymers could undergo hydrolysis, which meant that we could break them off. Whereas with the addition polymers, you can't do that. And so there are actually two types of hydrolysis you need to be aware of. Acid hydrolysis and base hydrolysis. And this is my first time I want to bring up the homework. I realized when I was doing the homework in the first page of it, I gave questions that were not Cambridge questions just to practice some hydrolysis. And on that first page, Q1 of the homework is all acid hydrolysis. In the last two questions, it doesn't mention the acid, so I just wanted to bring that up. Q1 of the homework for lesson 2 is all acid hydrolysis and should be treated as so. But we're going to go over both, and there are base hydrolyses in the homework. So if you'll recall, with the acid hydrolysis, you get an acid and an alcohol if I'm splitting up an ester, because you split this bond right there. And you have to treat water as if it's HOH. And then you have to basically restore the carboxylic acid and the alcohol that you had taken the water out of. You're putting the water back in. So the OH would always go to the carboxylic acid side, and the H would go to the alcohol side. And when you do hydrolysis, you always get two products. So notice that there are two products here. You start with one and you end with two. Could you hydrolyze and get more than two products? Yes, if there was more than one ester bond or more than one amide bond. And so one of the key differences you need to remember, this also comes from the AS chemistry class, is if I have a base hydrolysis, instead of getting OH, we actually get O naught. Because it's not in acid, so you don't get the carboxylic acid, you get the carboxylic salt instead, which is O minus with Na plus. You may recall that. The idea here is that you would put the Na with the O and the R with the OH. Literally looks like old school double replacement reactions from previous chemistry. If you recall from previous chemistry, you would do the double swap. It actually looks just like that when you're doing the hydrolysis with the base. So you have to remember, in base, you don't have the acid because you're not in acid, so you get the salt instead. And so what I did is the next slide is blank. It's blank on purpose because I want us to just practice a couple hydrolyses just to make sure we have the right idea. So I'm going to do skeletal because, quite frankly, it's easier. So how would we get our two products here? What would our two products be? So first of all, where do I split the molecule when I'm doing hydrolysis? You should point out, maybe with a different color, it's right there. That's where the hydrolysis takes place. It's at the ester bond. It's always the ester bond that gets hydrolyzed. You may want to point that out. Ester bond gets hydrolyzed. I think it's hydrolyzed with an S for Cambridge, though. So if you want to write it like Cambridge, you would do it. So then what we get is our products. If that's what's breaking, what goes on each side? It's not the H and the Cl we care about. That's just saying it's acidified, right? It's the actual water. And we put the OH on this side and the H on this side. So we end up with that as my two products.
And the Cl is just the catalyst? Like
The Cl is a spectator ion that's just hanging out.
oh. Then why is it necessary again?
It may or may not be written in questions. Because it could be HCl or HNO3 or H2SO4. It's just any strong acid could be used. And if preferential, you could just write H+. And then it doesn't matter which strong acid you're using. Let's try another one. What if I did this? What would this be? What do we do here? What are my products? Is there more than one ester here? So is there more than one bond that could be hydrolyzed here? Let's point them out. I'm going to point them out in purple.
Will both bonds get hydrolyzed?
I'm bringing this up because I did your homework. And then this happens in the homework questions. So this bond right there, right, gets broken, and that bond gets broken right there. And so when I write my products, I write them from left to right. So I'm going to write this one first. So this first one would be that line O, and what goes with the O? Would that be H or OH that I'm adding to this oxygen? H. Because that's methanol. And my next product would be this part right here. And if we have not what happened there? Somebody. Ramon.
I didn't realize
Whoopsie.
it's usually like automatically off.
Does that make sense for the middle part? Acid.
Probably a little early to ask, but if it doesn't specify that there's an excess acid, does only one of the bonds get hydrolyzed?
Assume they all do. Assume excess. That's a good question. And then this would be my last product. Are we okay with that? Okay. So anything that is got the double bond oxygen is getting the OH back to go back to a carboxylic acid. And anything that has just the single bond oxygen is getting the H back to go back to an alcohol. That's how we did hydrolysis last year. Let's try one more. This time let's do a base hydrolysis. So you missed the challenges last year? Can't wait to go back to them in Unit 6 when we do like the full set of reactions.
Just the best example.
Yeah, I need the best benzene.
That's not benzene.
Oh, never mind.
That's cyclohexane, right? That's not benzene. Okay. So NaOH and water. What do we get in here for hydrolysis products? Where does the split happen?
At the O?
At the O, single bond O, right? Right there. So I point it out just so that you remember, oh, that's what I need to do. And then here's where the break happens. But this time, instead of getting OH, you're going to get O and not, right? And then the other one gets the H. So I'm going to write my products from left to right. Believe it or not, this is smaller than the molecules you're going to work with. And that. Does that make sense to your products? What else can you write O not as? You can write it as O minus Na plus, showing the ionic character of it, because this is actually an ionic compound that you've made. This is a salt. They call it a carboxylate salt. Salt and alcohol. All right, so this is something that I need you to bring back. Like I said, your memory files from last year, you had learned how to do hydrolysis. So make sure you add that back into your files because we need to know that for today's lesson. So it's not only esters that can be hydrolyzed. this is what we had done before. All these reactions were actually from AS Chem. So if you got your flashcards, which hopefully you didn't get rid of, you can go back into your flashcards for AS Chemistry, and these reactions will be found there.
Right, didn't you?
We did hydrolysis of ester. Now we need to know you can also hydrolyze amides. So that's the new content. So amides are very similar to esters in look because remember ester was this, COOC. Amide is CON. So these bonds can be hydrolyzed exactly the same way. Where the ester bond gets hydrolyzed, the amide bond gets hydrolyzed, which is between the carbon of the double bond oxygen and the electronegative group right next door. Everything else would be exactly the same way, meaning that this is the bond that's broken. And then for your water, the OH goes to the carboxylic side and the H goes to the amine side. So whatever the alcohol did in an ester bond, that's what the amine's doing here, is taking the hydrogen. And the C double bond O gets the OH like before. Looking at this is actually, except for all the drawing we have to do later on, lesson itself isn't actually that long. But the homework is.
Keep foreshadowing.
I did the homework this weekend, that's why I know.
It's like Mr. Madison chapter like 30.
Not difficult, just a lot. Go back. Good? Okay. So propanoyl chloride. What would its displayed formula look like? Propanoyl chloride. How many carbons?
3.
1, 2, 3. What's got to be on one of the end carbons? It doesn't matter which end. Double bond OCl. I would just, most people write it to the right, but you could do it to the left if you felt like it. And then I'm not correct right now. What else do I got to do?
I get it, the hydrogen.
Hydrogens until every carbon has how many bonds? 4. Okay. So how could we hydrolyze it? Could we hydrolyze propanoyl chloride? Where would that happen? It wasn't mentioned on the last slide, but something was mentioned about acyl chlorides. That should give you the answer. And we'll do an acid hydrolysis, H plus and water. What would that be?
You break the double bond between C and O, and then add a hydrogen to O and the C.
So this is where the bond would break
Oh,
between the carbon of the double bond oxygen and the carbon with the electronegative group. That's where it would break. So what would go on either side for water? The OH is going to go to the side, and then the H is going to go to what side? Or. So what would my products be? Carboxylic acid. Again, every single time this hydrolysis process gives us a carboxylic acid. And then the other product would be just HCl. Right? Because the Cl goes with the H. That's fine. We're good? Question?
What's splitting matter?
Aqueous.
It's no
These are all aqueous reactions. Okay. Ooh, the next slide, we get a paper 4 question.
That's check mark. Oh, I know. Looked at this.
So this was a textbook question. Basically saying whatever you do to esters or amides, you can also do the acyl chlorides because they all look very similar to each other. The next question is paper 4. Now, I did have something to say about these questions. It's originally on the homework. So you can skip question 5 on the homework because I realized, trying to think about my past self in the summer who was making the workbook for you, and I put 11 questions on your homework for today. And I was like, wait a second. As I was telling you, I was like, I didn't put enough into the lesson. I put too much in the homework. So I took this question and I put it from the homework into the lesson. I was just grabbing all the questions I can find on this topic. And so your homework will still be 10 questions, taking out question 5. So skip question 5 on the homework because this is it. We're going to go over it together. If you want to do it again, you can, but the last part of question 5, technically, you haven't learned yet. I also realized, so it's like, just skip question, the other part. All right, so it's capsaicin. Does anybody know what capsaicin is?
Isn't it the spicy thing?
That's the spicy stuff, right? That's like a it's like a pepper, right? I don't know. I don't like spice. But it's like, if I saw this, I wouldn't eat it. I'm like, oh, ingredient capsaicin, no thank you. So it's this. Capsaicin is heated with an excess of hot, aqueous, NaOH. That's important. Whether it's NaOH or if it's HCl, gives you 2 different answers for your products. And so they tell you here, it's heated with hot aqueous NaOH. Draw the structures of the 2 organic products, H and K. And then this is common on an A-level test where the way they tell you which product they want is they give you the chemical formulas of the 2 products. And so what I did was the first thing is break that bond. Which bond do I break? Where is the bond that gets broken here? What's hydrolyzed, Caesar?
Okay.
Which one? The peptide bond, correct. Which technically isn't a peptide bond here because that's not a protein. That's why it's very careful with it's the amide bond, right? So it's the amide bond. In a protein, it's called peptide bond, but it's the amide bond. That's what gets hydrolyzed, which means that my 2 sides are left and right. The next thing I did was I counted my carbons to see, well, which one do they want here and which one do they want here. I'm happy to share with you that they put the left one here and the right one there. They didn't trick you with that, but when I was doing the homework, I was like, let me just double check that. So 1, 2, 3, 4, 5, 6, 7, 8 carbons there. That's 8. And here it's 1, 2, 3, 4, 5, 10, right there. So it's that way. The way that they present the questions to you is the way you should format your answers. So here I would not be switching from skeletal to display. I don't think that's I don't think that's worth it. I would rewrite this in skeletal. So there's a trap here. OH is also an acid because it's a phenol group, which means not only is it going to be hydrolyzed, this molecule, but this is going to undergo an acid-base reaction. And so let's take a look at how that would give us our products. So the first one would be, I'm going to start with my benzene ring. This is an ether, does nothing, not relevant to us. I've got my NH. And what else should go here? What should this be getting? What should this side be getting? Just a H, right? This should be getting the H and this other side should be getting the ONA. So then H. And I'm going to write the new H in purple. So you recognize that, oh, that's the new one. But here's the problem. This right here is an acid. And I put it into a base solution. So what should it also be doing, Ramon?
Reacting with the base, so.
It should be reacting with the base, which means what happens to that H? It goes bye-bye, it gets donated. And so this is why they have the nothing. Notice that an NA is there, but we don't have an NA here. Because this is technically O minus and NA plus. That's the ONA, is at the phenol. Because that's an acid-base reaction. So that's the new part there. And the clue there was to see that there's the Na that they told you. They're like, hey, there's a sodium here. And you wouldn't have got that if you didn't know the information I'm sharing with you now. What about the other side? What would that be? Count your carbons. I went like this 1, 2, 3, 4 to get my carbon chain to make sure I did things in the right spot. And so I started with this. 2, 3, 4, 5. To make sure I put my double bond in the right spot. And what goes on this side? What's added here on this side? Because it's in base. It's a double bond oxygen. It's not OH because it's in base. It's instead O na. And they give you that clue again here that they've got the Na in your product. So O minus and Na plus. Done. You have to put the plus minus charges? No. You could just put NaO and that'd be fine. But the plus minus charges do tell you that that's a salt. And it's an ionic compound. How are they awarding the marks here? Just one for each correct box. What are the two types of reaction? Because there's two going on. Acid base was one of them. And the other one's hydrolysis. And you have to get both of those right, so one. So this once again was the question 5 that was in the homework that I'm telling you not to do. Unless you want to rewrite it over again as practice and then double check your answer. And then the other part of that question 5, don't do it either because it asks about how LiAlH4 reacts with an amide, and you haven't technically learned that yet. So, I mean, you can go over it with me in home tutoring if you want, but we don't have to do it. Okay, so that's hydrolysis. We finished the hydrolysis topic for the day. So now we're going to move on to the second topic for the day, which is amino acids. Hello, biology. So, in the AS chemistry curriculum, when I first started teaching this class back in the olden days of 2013, there was a lot more biochemistry in this class, and Cambridge has been steadily moving the biochemistry components over into AS Bio. So AS Bio has, you know, a strengthened biochemistry component, and then this class, they're more focused on the actual reactions and putting things together. So this is one of those few areas of biochemistry that has remained. What used to be in this class that's been taken out, there used to be a bunch of stuff with DNA in this class actually, where you would do like the base pairing, the A to T and the G to C, that type of deal. There used to be some of that stuff in this class, but they've left us with proteins and amino acids, which is one of the macromolecules that you would study in ACE biology or another biology class. Technically, all condensation and hydrolysis reactions are most of the biochemical reactions that take place in biology. So if you understand condensation and hydrolysis, you'll understand most of the reactions in biology quite well, because most of them are either just some variant of a condensation or a hydrolysis. That's how we link monomers together or take them apart. Amino acids. You should memorize the general structure of an amino acid. They're usually presented to you in questions, but I think you should get familiar with the general structure and what it means. What does it all mean? In an amino acid, you've got a chiral carbon in the center. This is a chiral, typically chiral. There's only one amino acid it wouldn't be chiral with. Our group is just the hydrogen, but usually it's a chiral carbon. And this right here is an amine group. And this right here is the carboxylic acid. And the reason why they're called amino acids is because you've got the amine group and the carboxylic acid always on an amino acid. So there's 3 groups on an amino acid that are always the same. The amine group, the carboxylic acid, and a lone hydrogen. Those 3 groups are always the same. And then the R group is the only group that changes. There are 20 essential amino acids that our body needs to make proteins. I think it's 11 of them we produce naturally, and 9 of them we have to get through our diet, like through the foods that we eat. And then if you eat, for example, meat, that all meats give you all 20 that you need. But if you are a vegan, then you don't eat meat. So you have to balance like your legumes and beans and different things that will get you to all your amino acids, because those foods are incomplete proteins, meaning that they don't have all the ones you need. So you have to pair up different ones. So people who are vegan have to watch what they eat carefully in order to maintain, their protein and like muscle building, stuff like that, because you do need those proteins. Not that it's ethics is a whole different issue. We're not discussing ethics here, meaning people who are vegans do that for a personal choice, and I respect it. And it's just that that's something nutritionally that you have to be careful with if you are a vegan. And so amino acids, one of the interesting things about them is they're both an acid and a base. So they would be classified as amphoteric, just like water. So in a Bronsted-Lowry acid reaction or a Bronsted-Lowry base reaction, you can treat them as an acid or a base, depending on which one you're combining it with, an acid or base, which is one of the reasons why I mentioned acid-base reactions at the beginning of this lesson, is because amino acids can function as an acid or base. Now, I mentioned there were 20. There are 20 essential amino acids. You do not have to memorize them for this class. You would not need to memorize them in ACE biology. If you did take biochemistry in university, you are very likely going to be required to memorize all 20. And by all 20, I mean all 20 side chains, all 20 different R groups you could have. There's quite the possibility. A lot of teachers do make you memorize that because they give you coding for proteins. I don't know if you remember, like codons, anticodons, all that stuff from biology. If you're going to take ACE bio next year, it's something you definitely go over. You get these little abbreviations, and they tell you what protein or what amino acid is being coded. In your, I think I want to say it's your mRNA, does that work? Name, structures, and abbreviations of some amino acids. And so in this class, you're going to see either the name, the 3-letter abbreviation. I never see them use the 1-letter symbol, but I've seen a lot of questions with the name and the 3-letter abbreviation. And then what is the structure of the R group? Do you have to memorize these? No, they will be given to you in the questions. You just have to make sure you're looking at the right one. Now, I would note which of these are acidic and which of these are basic groups. Are there any of these groups that you can point out that definitely are acids?
Tyrosine.
Tyrosine is an acid. We may want to point that out there. That's an acidic group. And what other amino acid group is
Aspartic acid.
aspartic acid? That's an acid. There's still one more. Glutamic acid. So all 3 of these amino acid side groups would behave as acids. They give away their H plus by definition. And which of these are bases? There's at least one.
Lysine.
Lysine. And although some of you may say, oh, serine could be one. Again, I was saying alcohols are very close to neutral. They're slightly basic, but you usually will not lose that H plus or gain an H plus there. You usually say that is. All right, I printed this for you for a reason. You're going to need this for the homework. Need this for homework. If I gave you a question that was before 2022, which I'm sure I put some questions before 2022 in the homework, this information would be located in something called the data booklet. So the data booklet was taken away. Bye-bye data booklet. But the information in the newer questions is always found in the question. So pros and cons. The next thing we're going to talk about now is a vocabulary word. It's called the Zwitter ion. And I'm probably saying it wrong, but that's what it is. And some people think of it, there used to be a thing called Twitter. It's now called X. And they would think of it like the Twitter ion. No, it's the Zwitter ion. And so the Zwitter ion is when you have an amino acid that is dual charged, meaning that the Zwitter ion for an amino acid always has the amine group has been gained at H plus, and the carboxylic acid gave away its H plus. This automatically happens when you place an amino acid in water. When you place an amino acid in water, any amino acid, so this is the idea. If I take an amino acid, just a random one, needlessly glycine, and I put it in water, so I make it aqueous. It's its own acid and it's its own base. So the acid does what an acid does, and what does an acid do? Donates H plus. So this carboxylic acid will give its H plus away. But to what? Acids give their acids away to bases. So where does it give the H plus to? The base on the same molecule. So the H plus transfers from the carboxylic acid to the amine group. Yes, absolutely.
Amino acids are already like aqueous.
No, they could be solids. Like when you eat an amino acid, if you were to eat an amino acid in like a bean or like, meat or eggs, it's likely not to be in the aqueous form. It's likely to be in a solid form to start. But in your body, amino acids would be, well, you're mainly aqueous. So as it goes through, into your stomach, that's an acidic environment where your bonds will get hydrolyzed for your food, broken up into small pieces, and then go through the rest of your body. But do you see what I'm pointing out here? Literally, the acid is giving its H plus away to the base on the same molecule. And so that's why it's amphoteric, is because it both functions as an acid and a base. And so when we place this in water, we get this H3N. It's got that extra H plus, so now it has the plus charge. And then this. What is the overall charge of a Zweiker ion? Yeah, the overall charge is 0, right? Even though it is charged, the overall charge is 0. Yes.
Would it have a harm?
Would it what?
Like,
I
yeah,
would
no.
hope that proteins are largely harmless to eat.
Okay.
Yeah, we need that. That's an essential. It's an essential nutrient. It's fine.
Looking at what
It's not dangerous.
is charged molecules inherently bad?
It's table salt fat and A plus Cl minus.
Okay.
No, they're not. I mean, an excess of anything could be. Thank you. All right, Analia. It's your gold ribbon. Woo! You were here on Friday. That's what they're. No, they're not. Just because something has a charge doesn't mean it's bad for you.
Okay.
That will stop that discussion. I think there is fine. Okay, so at a neutral pH, and it depends. This is called the isoelectric point. Different amino acids exist as a Zwitter ion at different pHs because it depends on whatever your R group is. So the R group influences the pH of the isoelectric point. And what is isoelectric point again? That's the pH at which you have a neutrally charged amino acid where your Zwitter ion exists. That's the isoelectric point. So that's the intermediate pH for whatever that amino acid is. It could be 7, but it may not be 7 because it depends, like I said, on what the R group is. In one of your homework questions, it'll say that the isoelectric point is 5.5. So if it was 5.5, that means that anything under 5.5 would be low pH, and anything over 5.5 would be high pH. And so what you're going to need to recognize is what happens at a low pH than the isoelectric point, and what happens at a higher pH than the isoelectric point. So whatever this pH is, that's our center. So at a lower pH than the isoelectric point, what would happen to the amino acid? What does a low pH mean?
Acidic.
That means that there's lots of excess H plus in your solution. So how would that affect the structure of your amino acid? What do you think? I mean, it says it up there, but what is that trying to tell you? All groups will exist in the acidic form. What does that mean? Any bases will gain an H plus. Any acids will keep their H plus. So that means that because amines are a base, NH2 is a base, So it gains H plus at low pH. Carboxylic acid is an acid. It retains being an acid at a low pH. So any group that is classified as acidic or basic will be in the acidic form, the one that has gained the H plus. That's why in the beginning of this class, I went over what groups were basic, what groups were acidic, because of this information. Yes, Axel.
The H3 to become like H4 or something.
No, because then it wouldn't be attached to this molecule anymore. It would break the octet rule. That goes to this idea. If this is NH2, right, with a carbon, NH3 is an H plus coming in here.
Right, I forgot about the log pair.
Then, if we had NH4, what you would be saying is this. And I'll have some nightmares over that. Right, Daniel?
But can't phosphorus do something similar?
Very nice. Much proof.
No, it's wrong. Does that answer your question, Atsa?
Yeah, but can phosphorus make like 5 bonds?
Yeah, phosphorus is in. First of all, we're not talking about phosphorus.
I'm just asking.
Organic chemists largely are like ignored until we talk about DNA, because phosphate is in DNA. But we're only talking about literally carbon, nitrogen, oxygen, and fluorine. All of those 4 cannot break the octet rule. Phosphorus can break the octet rule. So yes, pH 5 could exist, but not N. Not nitrogen.
Why did and do?
Because nitrogen does not have access to d orbitals.
Okay.
Is the quick answer. Because when you have energy level 2, you only have S and P. There is no D, so it maxes out at 8. Like, there's no more story to that. Like, it just doesn't do it.
Okay.
That's why organic chemists only need to count to 4. 4 bonds. No 5 bonds. For like, the half a millisecond?
But that is, it does exist.
Half a millisecond. Part of a millisecond. Anyways, are we okay with what I've said so far here? All right, what about high pH? What does that mean? What does high pH mean about your solution? Instead of having lots of excess H plus, you will have lots of excess OH minus in your solution. So this is basically the same in basic conditions, or that if we were reacting with NaOH, what would that look like, right? Lots of excess OH minus in solution. So practically, what does that mean for our amino acid? What would all groups exist in? If they're an acid or a base, which form are they going to exist in? So all groups would exist in basic form, which also means lose H plus. And the other one would have been, instead of lose H plus, it would have been all groups gain H plus. If they're a base, they gain the H plus because the H plus is there. The idea is that if you're in a solution that has a lot of excess H plus, that H plus is going to whatever group it can. And if you're in a solution that's in excess OH minus, then all the acids are giving away their acids. That's what's happening. So the reason I'm spending so much time going over this is one of the things you're going to have to do is draw amino acids at the isoelectric points, at a low pH, and at a high pH. And this lesson won't be done today, because next class we actually have to learn how to separate these amino acids based on these differences, like how they're drawn. That's what that process of electrophoresis is, that fancy word. That's next class's lesson. Okay, so I've done a lot of introduction now on amino acids. Let's take a look at our first practice question from the textbook. It says, what is the general structure for a 2-amino carboxylic acid? The general structure. This is just draw out what a regular amino acid looks like. Be in the middle. Doesn't matter which side you put your amine and your carboxylic acid on.
Since it's kind of we get optical isomers.
I put a question in your homework with optical isomers with an amino acid. So yes, it does. I found one.
I want people to really
There are. So it doesn't matter which side, because it's 4 sides, so you can put them on whichever side you want. NH2 goes on one. Typical format is just to put it like this. Do I have to write COOH or could I write it as CO2H? Could I write it like this? Do you remember that? And then H, and then we don't know what that is, so we call it the R group. And the second question I thought was unique from the textbook. I think this is a good question. Why are all amino acids solid at 20 degrees Celsius if they're not in water, right? Why are amino acids solid at, I think our room is colder right now than 20. It's a pretty cool thing. But usually this classroom runs around 20. Yes. Because of several hydrogen bonds. Because it makes
Because me.
of its ability to hydrogen bond multiple times. Which is a strong force of attraction. So it has pretty strong forces of attraction, multiple hydrogen bonds, so it's going to be in the solid phase amino acids. Yes, you can take them, put them in water, make them aqueous. Some of you may do that with protein powder. Protein powder, right? And proteins, by the way, are like 50 of them linked together. That's why proteins are definitely solids. If you move on to another biology class, you'll learn something called the primary structure of proteins, the secondary structure of proteins, the tertiary structure of proteins, and the quaternary structure of proteins. Something you may or may not remember from forever ago when you took honors pre-ACE bio, but it starts at the amino acids and how they link together. All right, so draw this carboxylic acid, which is an amino acid called serine, in which the R group is HOCH2. So C in the middle, H2N, CO2H, H, and what goes on the bottom? What's the R group? They told us in the question. Does it connect at the alcohol or does it connect at the carbon? It connects at the carbon. Draw the structure of the zero ion of serine. So what would that look like? So how would we draw that? We place it in water, that is isoelectric point. So you're going to take this hydrogen and move it over here. Which means how many hydrogens would now be on the amine? 30. So what charge will it take? Plus. And you must write the charge. If you don't write the charges, it's not going to be considered correct. And then here, this would be CO2. What charge? Lost the hydrogen with the plus charge, so what does it have? Minus charge. That is their ion.
Hey, what is sweeter ion cake?
It's a German word. And I had someone who was a German student a couple years ago, and they were like, yeah, it makes sense. I think when he said you could look it up, is it meant that the charges canceled or something like that? Or like it was dual charge, something like that.
It's either meaning hybrid.
Hybrid. Okay, so it's somewhere around the,
Yeah.
it was somewhere around that idea that it has both charges, plus and minus. Because when I said when my German student was like, yeah, it makes total sense. And everybody else in the class was like, we have no idea what that is. So if you know the German language, it could help you out with this. I have to look up the scientists who, originally figured this stuff out. It's probably in the 1940s, somewhere in there. All right, continued. Draw the structure of the ion of serine that would be present in acidic conditions. So that means low pH. So what would we do to this at low pH? Francesca. Yes. Anything that can be acidified must be acidified. So that means that this right now that it's existing in a basic form would have to also turn into an acidic form, and you would leave this alone because it's already the acidic version. Absolutely correct. So just rewrite this, except instead with CO2H. So it's H3N plus H, CH2OH, and CO2H. And some of you might say, well, if alcohol is slightly basic, why isn't that also gaining an H plus? Because it's only slightly basic. Alcohols should stay untouched. Not acidic enough. Maybe at a low enough pH, they don't specify, but at an extremely low pH, maybe you could get an extra H on that alcohol. You'd have to look up what that is. Draw the structure of the ion of serine in alkaline conditions. So Cambridge does expect to know alkaline is the same thing as base, which means high pH. So what should I be doing to my molecule at high pH? What would I do? What would it look like? The same molecule at a high pH. Instead of adding a hydrogen, you take the hydrogen away from anything that's currently acidic. So if I start with this one as my Zwitzer ion, at a high pH, this is going to lose its H plus to the solution because all the OH minuses in the solution are going to steal the H plus from that, basically. So you end up with H2N, C, COO minus, H, and CH2OH. Notice that how at this low pH, this is no longer neutrally charged. What charge does this have right now? It has an overall, what charge? +1. And what is the overall charge in the alkaline conditions of my amino acid? Overall charge is -1. And the reason I'm pointing this out is foreshadowing, because we need this for next class's lesson. Because when we do electrophoresis, it's actually separating amino acids based on the charge and size difference. So like, what is the charge of the amino acid and what's the difference in size? And so this is kind of like just a foreshadowing that you're going to need to be able to do this in order for that last standard that we're not getting to this class. Yes? No, it just means it would be attracted to something with a positive charge. So if you have a source of, positive charge, then it's going to move towards that. Okay. So our groups in these amino acids, alanine and valine, are CH3 and CH3-2CH. Draw these amino acids. So we're getting to our last major objective for the day. So draw each of them. Alanine is this one. I'm going to do that one first. So CH3? Yeah. H2N COOH. Why do you think I'm expanding out my carboxylic acid? Because the next question is going to ask, give an equation to show the formation of a dipeptide made from these two things. So I'm going to go over how to do that. So I've got my alanine, and now I'm going to get my valine. So I'm going to expand at my amine group here. You don't have to write the unshared here. I just wanted to. This is CH3. Okay. So these are my two amino acids. And so the question then becomes, how do I bring them together? How do the amino acids link with each other? Because that's actually how you build the first layer of a protein, is you link, I mentioned 50. You would link like 50 of these amino acids together. So how does that happen? What would happen here? Isn't it just a condensation? So forming a peptide bond is just a condensation reaction. I'm putting AS Bio alerts because you'll have many condensation reactions in AS Bio, and they'll all have different names, but it's literally the same thing. And what is that same thing that's happening? What do you have to do to link these two together? Take out. So take out H2O. And you do have to know where you're taking out the water from. So from the carboxylic acid, I face these toward each other this way on purpose. From the carboxylic acid, what am I taking out? COH. And from the NH group, I'm taking out the H. So that stuff has to go bye-bye. And then everything else gets written instead of COO, it's CON. And so that's what we're going to write on our next slide. The way I have it for you all is I put them on the same paper, so it's easy to see what your results are going to be. I just switch the slide though. So I did this. H2N, CH, CH3, and then it's CONH, CH, CH3, 2CO2H. This is the dipeptide. Now I want you to notice something. This was linking 2 amino acids together, right? We linked only 2 amino acids. Is this the same thing as making an infinite condensation polymer, like we did last class? Yes or no? There's similarities and differences. We're taking the water out, just like we did with condensation polymerization. But is this a polymerization? Is this where you're making an infinite amount with a repeating unit? No. You're not taking out from the ends. You're only putting 2 together to make a larger amino acid called a dipeptide. So could you put 3 together for a tripeptide?
I think so.
Could you put 20 together? Where's Cambridge asking for us to be able to do? Go back to the standard. Go back to the early standard in the beginning of the lesson. What are they asking for us to be able to do? Because that should be our guide. Okay. It says,
Oh, dying.
describe the formation of amide bond. Peptide bonds also known between amino acids to get dipeptides, which I just showed you how to do, and tripeptides, which would be for 3. So that means specifically they're either going to ask you to draw 2 amino acid units where you link together or 3 amino acid units. So they would not give you a question that link 1 together. Yes. You can show them go. Yes. Okay. Okay. This question, I wanted to show you to say that even though a dipeptide and a tripeptide itself is not a condensation polymer, could you be asked to polymerize amino acids? Do they have the ability to polymerize? The answer is yes, they do. You just have to be careful of the context of the question. So let's take a look at this question. The isoelectric point of asparagine, sounds like asparagus, but it's asparagine, is 5.4. You see all kinds of fun things in science. 5.4. What does that mean? Why is the isoelectric point important? Why do we care about that? Go ahead. Go ahead, Sabrina.
Because that's how it's gonna be hard to go through the high
Compared to that.
Yeah.
So that pH is where the Zwichter ion exists, where you have the Zwichter ion and then everything else would just be normal. So it has no overall charge. And so how do they want us to write that as a response? You can write the pH at which the Zwitter ion exists. And that's it. That's good enough.
Yes.
Or the overall charge is 0 of the amino acid is the other way you can write it. That's the first mark. I was doing your homework, and in this section, they asked that define or describe what an isoelectric point is 3 times in 3 out of the 10 questions. It's describe, define, define, describe. So would I say that this is one that could definitely show up on your paper 4? This is a definition I've seen many, many times, so that's definitely one that could show up on your paper 4. It's not a hard mark to earn. Just remember that it's a common one, so you may want to put it on a flashcard when you're revising for the end of the year. Draw the structure of pH of 1. So what does that mean we have to do? What does pH 1 mean? That's pretty acidic. That's way more acidic than a pH of 5.4. So you compare 1 to 5.4. 1 is lower. I know that sounds silly, but it is, which means we are in a low pH situation. So one is lower, which means low pH, which means excess H plus. Excess H plus, give H plus to everything that can take it. Meaning all bases must transfer and become instead acids. So what does that look like here? What is this? Is that an amine, yes or no?
No. Yeah. It's not.
This isn't amide. Why is that important? I mentioned it at the beginning. Amides are not bases. That's a trap. This is a trap. Amides are neutral, which means they will not gain or lose an H plus. Make that a little note. Do I have any bases here that could gain an H plus?
Yeah.
This right here is an amine. So because it's a basic group, it can gain an H plus. That's the only one I see. So my answer here is going to be H2O, CO, PH2, CH, NH2, NH3 plus, and then COOH.
So that's
Draw that prettier. NH3 plus. So what did I have to know here? The only basic group is the amine. The amine will gain an H plus. Amides are not basic. Amides are neutral. All right, so that's the first mark for this. Asparagine can polymerize to make polyasparagine. Draw the structure of this showing 2 repeat units. That means showing 2 monomers here. Because it's the same one repeating over and over again. And here, the peptide linkage should be shown displayed. So whatever we call the peptide linkage, we should show that fully displayed. So how do we do that? I'm going to try to tell you how I've been drawing because I've been doing it like this for the homework. The carbon that matters is this one. That's where the polymerization is going to happen. Why is that one the one that matters? In a condensation polymerization, you need a carboxylic group, right? The C double bond O, and you need either an alcohol or an amine. So I basically redrew this out as carbon. I put the NH2 on one side. It doesn't matter which side you put it on, but I put it here. So I redrew it out. And then I put my carboxylic acid on this side. I put my H on a third side. And then all of this stuff I wrote at the bottom like this. CH2, CONH2. Does that make sense? This is me redrawing this molecule in a way that makes sense for polymerization. This carbon is the circle one. This is where you gotta make sure you're paying careful attention because how you draw it, if you don't understand it, it's gonna look very confusing very quickly. Welcome back.
Is that chirality?
It's a chirocarbon, but there's free rotation, meaning that I can put these 4 groups on any 4 sides I technically want to. And that's why you gotta be careful because if you draw it wrong, it's gonna be a lot harder to polymerize it, or if you draw it in a way that's hard for you to see. And so I'm gonna rewrite this a second time. Why? And yes, if you can do this in your head, good for you. Is what I'm gonna say. I have to draw it out. Not only when explaining it, but when doing the work myself, I actually have to draw it out. Do you agree that this is the same molecule just written a second time? How do we polymerize it to get a condensation polymer here? What are we taking out? From the middle, what comes out? The OH and the H. But because it's a polymer, what else are we taking out? Because it's poly. That doesn't mean it's a di or a tripeptide. That means it's infinite. Well, not technically, but it goes on thousands and thousands. So what else comes out? The H from here and the, oh wait, are we okay with that? So then we have to draw our product. Like what do we still have from that? I would start with my line here and my stuff, NH, CH, CH2, CONH2. Could you draw that skeletally as well? Sure. However, it works best for your brain. CO, N. Can you draw this out? Structural or skeletal for the mark.
What?
Isn't this the peptide bond? So you have to clearly show that. CON, and then H, and then the same thing. H, CH2, CONH2, C double bond O, and it keeps going. How many marks is this worth? 2. What are the 2 marks for? One of them's for getting this part right, like where the linkage happens, and one of them's for the outside part. I overheard in the bell work, someone say, not saying who, I don't even remember who, but I overheard someone saying in the bell work that this was a ketone. Is it a ketone? No, because what's the thing that comes after this? Isn't this repeating again and again and again? So what would the next thing be actually? A nitrogen, right? Which means that this isn't amide. So be careful when you're looking at polymers. Just be careful when you're looking at them, is what I'm saying. You could misidentify your functional groups. I think that's the last part of this nutrition. Woohoo! So the last part is not really intentional, but this was a paper part. So the moral of my story here is rewrite these molecules in a way that makes sense for you when linking them together. That's how I did all the homework. I can take a picture because I did like all the questions myself. I have the mark scheme, but the mark scheme is always just going to have the final answer, not how you put it together. So I can scan like me solving it, but after I post the homework too. All right, so peptide bonds. We talked about this. Amino acids, they link with each other. When they react with each other, and it's only 2, you make a dipeptide. If there were 3, you would make a tripeptide. This is a condensation reaction. You're taking out water. And this reaction continues and makes you polypeptides, which is the first layer of a protein. It's called the primary structure of protein. Is when you put your polypeptide together, which your body does this in your cell very well. You just for this class have to know how to make dipeptides and tripeptides. On the next slide is a jump scare.
There's no great having 10 minutes.
My God.
You're gonna have to memorize all that, Daniel. What?
So if this was a 3rd year biochemistry class, you would be likely asked to memorize all these by heart, all the R groups. This is not a 3rd year biochemistry class, so you do not. However, these are your essential amino acids. They're all being shown to you in the ether ion forms. And I think this is a selection of them. I might be missing a few. But this is a bunch of them. Notice they're put into categories: non-polar, polar, acidic, and basic.
It's like, oh yeah.
This is all determined by the identity of the R group. So the R group classifies what type of amino acid you have going on, whether it's non-polar, polar, acidic, or basic, has everything to do with what type of reactions it can do, what service it has to do in your body. So it all has to do with the body. And then how we form proteins. So a protein is actually a bunch of these put together. And so in a biology class, you would just see like this: val, lys, val, lu, like in your, and that's the 3-letter abbreviations for all the amino acids that are being linked together. And so at its understanding, it's the idea that I'm putting all of these together to form my polypeptides. And so yes, this is how it would be presented in a biology class, but the chemistry gives you the idea of, oh, that's what that really is. That's what I'm putting together in order to get these. Do you need to know this for this class? No. This is me just leaving some things that I think are helpful information on why do we care? Like, what does this matter for? Why am I doing these reactions? And so this is how it would look in a biochemistry class. You would have your N terminus N. What does terminal mean? The end of. And then this would be your C terminus N, your carboxylic end. That also means the end of on the other side. This is your system of lettering that they use in biochemistry. This would be 8 specific amino acids linked together. They don't show the whole entire structures usually in a biology class. They just give the abbreviations and they're like, you got that. You know what that all means. Because they ask you to memorize all these different amino acids.
So that's like inside of me.
Yeah, it's inside of you. What's all of that? All right, so can proteins be hydrolyzed? Of course they can. This is what your stomach does. It does it really well. And you can do this in chemistry by using a strong base or a strong acid and heating under reflux. What?
Not under.
Why do you heat under reflux? And this is the bond that gets broken. It would be the peptide bond. And that's it. So, homework. It is 5 pages front and back. Oh, I did it, I know. And so it will not be due on Thursday to give you some additional time. I'm going to give you the whole weekend to work through that and move on Monday. I also have tutoring both today after school and Monday after school. Today and Monday. But we are done with lesson 2. Let me go ahead and turn my recording off. How much chemistry we got here?